or maybe electricity flowing forever without losing even a single watt of energy. These sound like, well, far-off science fiction fantasies, don't they? But what if I told you they're actually realities? Made possible by a really mind-bending quantum phenomenon right here, right now. Today we're taking a deep dive into superconductivity. It's a state of matter that truly challenges our everyday intuition. And our mission in this deep dive is really to unpack this incredible journey of superconductivity, from its surprising discovery to the intricate physics that explains how it works, and then crucially, its current and potential impact on your world. We're going to travel from the coldest labs on Earth, quite literally, to the incredible and sometimes controversial promise of room temperature breakthroughs. It's a journey that will help you understand how this unique state of matter opens up entirely new possibilities. So let's get into it.
It's truly fascinating. I mean, how fundamentally different superconductivity is from what we typically think of as just a normal conductor. It's not simply a very, very good conductor. It's actually a completely new thermodynamic phase of matter. And there are two unique characteristics that really set it apart, and they're both absolutely essential.
Okay, and the first one, the one that probably springs to mind for most people, is the complete disappearance of electrical resistance. We're talking zero, like dropping to a value experimentally indistinguishable from zero below a specific critical temperature, DSC, which means basically no energy loss, ever. At least not in a direct current. It's almost perfect in a way.
Almost, yeah. And then there's the second equally crucial property, the Meissner-Ochsenfeld effect. This is the active expulsion of magnetic fields from the material's interior as it cools down and transitions into the superconducting state. It's what creates perfect diamagnetism, where the material actively pushes away magnetic flux lines. Now, the critical distinction here is really profound. See, a classical perfect conductor, if such a thing existed, would merely trap any magnetic field that was already there when it became perfect. But a superconductor actively expels it. This isn't just some neat trick. It's the definitive proof that superconductivity is a true quantum thermodynamic state. It's something totally distinct from anything classical physics can explain.
Right. And the story of how we even stumbled upon this quantum oddity, it really begins back at the dawn of the 20th century. There was this fierce scientific race going on, to explore matter at extremely low temperatures. Physicists back then had, three competing theories about what would happen to electrical resistance near absolute zero. Would it just drop smoothly to zero, maybe level off at some small value, or would it somehow, maybe surprisingly, increase? Nobody really knew for sure.
Exactly. And leading that charge, really at the forefront, was Heike Kamerlingh Onnes at Leiden University. On July 10th, 1908, he achieved something truly monumental. He successfully liquefied helium. This was an absolute game changer. It literally made his lab the coldest place on Earth, and it opened up an entirely new experimental frontier to investigate these very theories. And this foundational work, well, it earned him the Nobel Prize in Physics in 1913.
And it paid off pretty quickly. With liquid helium now available, Onnes and his team started systematically studying the resistance of highly purified mercury. They needed really pure stuff. Then, on April 8, 1911, as they cooled the mercury down, something truly astonishing happened. At 4.2 Kelvin, that's incredibly cold, the resistance didn't just gradually decrease like some theories predicted. Nope. It suddenly abruptly vanished. Gone. Onnes' notebook entry, it's famously terse, understood it. It just says, quick negenoig nul, which is Dutch for mercury, almost zero.
Yeah, almost zero. It was a genuine, abrupt phase transition, a complete surprise to the scientific community at the time. And to definitively prove this superconductivity, as Onnes initially called it, he did another decisive experiment in 1912. He induced a current in a superconducting lead ring. Then he removed the power source, and the current just kept flowing and flowing indefinitely. That's what we call a persistent current. And it was the unequivocal proof of a truly zero-resistant state.
So, okay, for about 2 decades, that was the main picture. A perfect electrical conductor. Simple enough, right? But then came what our sources describe as the next great experimental disruption. Something else was going on.
Indeed. Fast forward to 1933. Walter Meissner and Robert Ochsenfeld were doing experiments, and they observed that when they cooled a tin sample while it was already sitting in a magnetic field, the field wasn't trapped inside as you might expect for a perfect conductor. Instead, it was actively expelled as the pin became superconducting. This was the crucial anomaly. It fundamentally shattered that simple perfect conductor model. Because, like we said, a classical perfect conductor would have just frozen that pre-existing magnetic flux in place. So the Meissner effect really established superconductivity not just as zero resistance, but as distinct thermodynamic phase, something that needed quantum mechanics to explain it.
Okay, so once they knew what it did, zero resistance, expelling magnetic fields, and how it behaved below that critical temperature, the biggest mystery still remained. The fundamental why. How does this actually happen? And for almost 50 years, that question just lingered. How could this seemingly impossible behavior emerge from, ordinary metals?
Well, the Meissner effect really provided that necessary clue for the theorists. The first successful theories were what we call phenomenological, meaning they described what was happening and how it behaved, but without fully explaining the underlying why at the atomic level. The London equations, proposed by Fritz and Heinz London in 1935, were revolutionary. They offered the first quantitative way to describe how a magnetic field interacts with a superconductor. They defined a specific skin depth, the London penetration depth, lambda, which is the characteristic distance a magnetic field can creep into the surface. This was huge. It moved the field beyond just observation towards predictive science.
Right, putting numbers on it. And then the Ginzburg-Landau theory in 1950 took that understanding even further, didn't it? It introduced this idea of an order parameter, something that behaves almost like a wave function, but on a macroscopic scale, giving us a way to describe the superconducting state across larger distances. And this theory was incredibly significant because it predicted another crucial length scale, the Ginzburg-Landau coherence length, 11, and maybe most importantly, it predicted the division of superconductors into the two distinct categories we still use today, type I and type II materials. That work eventually earned Vitaly Ginzburg a shared Nobel Prize in 2003.
Absolutely. Yet the microscopic why, the real nuts and bolts of it, still eluded them until 1957. That's when John Bardeen, Leon Cooper, and Robert Schrieffer came along and introduced the BCS theory. Named after them, of course. It was a true breakthrough, finally explaining the underlying physics, and it earned them the Nobel Prize in 1972, Bardeen's second Nobel, actually.
Wow. Okay, so the profound insight of BCS was solving this mystery of how electrons, which normally repel each other, they're both negatively charged, right? How they could actually attract each other and form pairs. That sounds completely counterintuitive. How on earth did they figure that out?
It's a really ingenious mechanism. Think about an electron moving through the crystal lattice, the grid of positive ions that makes up the metal. As this electron passes by, its negative charge slightly pulls the nearby positive ions closer together. This creates a temporary region of slightly higher positive charge behind the electron, sort of like a wake in water, or maybe a temporary ripple or deformation in the lattice structure. This subtle positive wake then attracts a second electron. So it's not a direct attraction, but an indirect one mediated by the lattice itself. This interaction is mediated by lattice vibrations, which quantum mechanically are treated as particles called phonons, tiny packets of vibrational energy, like microscopic sound waves moving through the crystal. So at low enough temperatures, this phonon-mediated attraction overcomes the electron's natural repulsion, and they bind together into what we call Cooper pairs. And these pairs aren't tiny point particles, they're actually quite spread out over hundreds of nanometers, and they overlap extensively with many other Cooper pairs.
Okay, so these Cooper pairs, they aren't just floating around randomly then. They act together like a single coherent quantum entity, almost like a synchronized dance of electrons across the whole material.
It's exactly right. They condense into a single macroscopic quantum ground state. It's a collective phenomenon. This condensation dramatically lowers the system's energy, creating what's called a superconducting energy gap, often denoted by delta. This gap is absolutely crucial. It means there's a minimum amount of energy required to break a Cooper pair or excite the system. There are simply no available low-energy states for individual electrons to scatter into, which would normally cause resistance. This lack of available scattering pathways is the microscopic origin of zero electrical resistance. The BCS theory was incredibly successful. It correctly predicted the temperature dependence of the energy gap, specific heat anomalies, the isotope effect where T2D depends on the isotopic mass of the atoms, and even the Meissner effect. And there's more. In 1962, Brian Josephson, then just a PhD student, predicted that these Cooper pairs could even tunnel quantum mechanically through a thin insulating barrier separating two superconductors. This Josephson effect is now the basis for extremely sensitive magnetic field detectors called SQUIADs.
Okay, so we have this zero DC resistance, which is just mind-boggling, and these persistent currents, which you said are really the hallmark of superconductivity. You can induce a current, take away the power source, and it just keeps flowing, potentially forever. I mean, if you had a superconducting ring, you could charge it up and then just leave it. And theoretically, that current would still be there centuries later. That's truly wild to think about.
It is. It really challenges our intuition about energy dissipation. And that Meissner-Ochsenfeld effect we discussed, the expulsion of magnetic fields, it's the definitive signature of a true superconductor. It's not just passive shielding like a perfect conductor might do. It's an active expulsion, resulting in perfect diamagnetism. The magnetic susceptibility, Che, is exactly making one. And here's where it gets really interesting, connecting different fields of physics. The Meissner effect, this expulsion of magnetic fields, is actually a profound analogy to the Anderson-Higgs mechanism in particle physics. Within a superconductor, photons, the particles of light and electromagnetism, which normally have no mass, effectively acquire a mass. This mass causes the magnetic field to decay exponentially inside the superconductor over that characteristic London penetration depth, lambda. It's a remarkable example of how studying phenomena in cold bits of metal, condensed matter physics, can actually shed light on the fundamental workings of the universe, like particle masses.
That connection is incredible. So the superconducting state sounds almost magical, but it can't be invincible, right? What are its Achilles heels? Are there limits? Can we break it?
Oh, absolutely. The superconducting state is actually quite delicate. It can be destroyed if you push it too hard in certain ways. There are three critical parameters that define the boundaries of a superconducting state for any given material. First, the critical temperature, Tc. You have to be below this temperature for superconductivity to even appear. Second, the critical magnetic field, Tca. Apply too strong an external magnetic field, and superconductivity vanishes. And third, the critical current density, Tc, try to pass too much electrical current through the superconductor, and the magnetic field generated by the current itself can destroy the superconducting state. Exceed any one of these critical values, Tc, Hc, or Jc, and the material abruptly reverts back to its normal resistive state. We call this boundary in the THJ parameter space the critical surface.
Okay, so based on how they respond specifically to magnetic fields, you mentioned earlier we get these two distinct types of superconductors, type I and type II. And this distinction seems incredibly important for, well, actually using them in the real world.
It's absolutely crucial for practical applications.
Yeah.
So yes, type I and type II. Type I superconductors are, in a way, the ideal or simpler ones. They exhibit a perfect Meissner effect. They completely expel all magnetic flux right up until they reach a single critical magnetic field, HENC. At that point, poof, superconductivity is abruptly and completely destroyed throughout the material. These are typically pure elemental metals like the mercury Ohms first studied or tin lead. But the problem is their critical fields, HENC, are generally very, very low. Kamerlingh Onnes himself found this out the hard way. His early attempt to build a powerful superconducting electromagnet failed because the magnetic field generated by the magnet itself was strong enough to destroy the superconductivity in the wire.
Ah, okay. So if type I materials are kind of wimpy when it comes to strong magnetic fields, what about type II? They sound like they must be the ones we use for powerful magnets then.
Exactly. Type II superconductors are much more complex, but also much more useful for high-field applications. They have two critical magnetic fields, a lower critical field, Hc1, and a much, much higher upper critical field, Hc2. Below Hc1, they behave just like type I superconductors' perfect Meissner effect, expelling all magnetic flux. But between Hc1 and Hc2, they enter what's called the mixed state or vortex state. In this state, they make a kind of clever compromise. Instead of completely giving up on superconductivity, they allow the external magnetic field to penetrate, but only in discrete tiny tube-like filaments called Abrikosov vortices or fluxons. Each vortex contains exactly one quantum of magnetic flux, H2E, and has a core region that's essentially normal non-superconducting metal surrounded by circulating supercurrents that screen the field elsewhere.
So by allowing these controlled leaks of magnetic field through these tiny vortices, the bulk of the material can somehow stay superconducting even in much stronger fields.
Precisely. This partial flux penetration, these vortices, allows the material to minimize its overall energy in the presence of a strong field. It enables the bulk of the material between the vortices to maintain zero resistance up to that much higher upper critical field, Hc2, which can be hundreds or even thousands of times higher than the HEC for type I materials. This is why type II materials, which include most superconducting alloys like niobium titanium, niobium tin, and also the high-temperature superconductors, are absolutely indispensable for practical high-field applications like MRI magnets and particle accelerators, and what determines whether material is type I or type II. It ultimately boils down to a dimensionless material parameter called the Ginzburg-Landau parameter, kappa, which is the ratio of the magnetic penetration depth to the coherence length. If kappa is small, less than 1 dov, it's type I. If kappa is large, greater than 1 dov, it's type II. It's related to the energy cost of forming an interface between normal and superconducting regions.
Fascinating. Okay, so what kinds of materials are we actually talking about here? It sounds like there's a huge variety, stretching from Onnes mercury all the way to today's cutting-edge stuff.
There truly is a vast and diverse landscape. We can broadly categorize them. First, we have the conventional superconductors, the ones generally well described by BCS theory. These are often called low-temperature superconductors, or LTS. This group includes about 27 elemental superconductors found on the periodic table, like niobium, Tc 9.25 K, lead, 7.2 K, and the original, mercury, 4.2 K. But their TCs are quite low.
Right, and then you mentioned the alloys, which you said earlier are the real workhorses for many practical technologies today.
That's right. Within the conventional LTS category, alloys are dominant. The absolute champion is niobium titanium, NBTI. It's a ductile alloy, meaning you can easily draw it into long wires, which is crucial. Its TZI is around 10K. NBTI is used almost ubiquitously in things like MRI magnets, and it formed the backbone of the main dipole and quadrupole magnets for the Large Hadron Collider at CERN. Then there's niobium tin, NB3SN. Its TC is higher, around 18K, and it can handle much higher magnetic fields than NBTI, up to maybe 23 Tesla or more in applications. But it's an intermetallic compound, very brittle, which makes manufacturing wires much more challenging. It's used for more specialized high-field magnets like upgrades at the LHC or in fusion energy research.
Okay, so those are the conventionals. But the real revolution, the thing that got everyone excited and where high-temperature superconductivity, HTS, entered the picture happened in 1986. That really shook things up, didn't it?
Yeah, it absolutely did. A complete paradigm shift. In 1986, J. Georg Bednorz and K. Alex Miller, working at IBM Research in Zurich, made a stunning discovery. They found superconductivity in a ceramic material, a lanthanum barium copper oxide, at around 35 Kelvin. This was revolutionary for two main reasons. First, ceramics were generally considered insulators, not materials you'd expect to superconduct at all. Second, 35 Kelvin absolutely shattered the previous record TC, which was about 23 K for NB3G, and seemed to defy the theoretical upper limits predicted by simple BCS theory at the time. This discovery earned them the Nobel Prize in Physics just 1 year later, in 1987, remarkably fast recognition, and it ignited what reporters famously called the Woodstock of physics, a period of incredibly intense, frenzied global research activity.
Wow. And that quickly led to materials with even higher transition temperatures, crucially getting above the boiling point of liquid nitrogen. That felt like a massive practical leap forward, right? Making cooling much easier and cheaper.
It was a huge practical milestone. Just months after the Bednorz-Miller discovery, researchers found yttrium barium copper oxide, usually called YBCO or YBACUO, which superconducts at around 92 Kelvin. This was monumental because 92 K is significantly above the boiling point of liquid nitrogen, which is 77 Kelvin, negative 26 degrees C. Liquid nitrogen is vastly cheaper and easier to handle than liquid helium, which boils at 4.2 K. Suddenly, the prospect of application seemed much more attainable. These copper oxide-based materials are called the cuprates. They're complex, layered ceramic materials, and their superconductivity often depends sensitively on chemical doping. Other cuprates were discovered later with even higher TCs at ambient pressure, with the record currently held by a mercury-based cuprate, Hg1223, at about 134 Kelvin under normal pressure, and even higher under applied pressure. We also have other families of unconventional superconductors. The iron-based superconductors, or IBS, were discovered around 2006. They're also layered materials, often containing iron and arsenic or selenium, with TCs reaching above 50 Kelvin. Their mechanism is also thought to be unconventional, not simple BCS. And there's a somewhat unique case, magnesium diboride, MgB2. Discovered in 2001, it has a TC of 39 Kelvin. While relatively high, it's now considered mostly a conventional BCS superconductor, which is a particularly effective one, mediated by phonons. But its TC is much higher than conventional alloys like NBTI or NB3SN, making it very promising for certain applications where you need something between LTS and HTS performance and cost.
And then pushing the boundaries even further, we have these materials called superhydrides. They sound like something straight out of a high-pressure chemistry lab trying to achieve the impossible.
They really are quite extreme. These are compounds extremely rich in hydrogen, synthesized under incredibly high pressures. They are the current record holders for the highest confirmed critical temperatures. For example, a lanthanum hydride, LaH10, showed superconductivity around 250 K, but only at pressures near 170 gigapascals, GPa. That's over 1.5 million times atmospheric pressure. More recently, a carbonaceous sulfur hydride, CSH, was reported to superconduct at up to 288 Kelvin, that's 50 degrees Celsius, basically room temperature, but only under even more immense pressures, exceeding 267 GPa. Interestingly, despite the incredibly high TCs, these superhydrides are actually thought to be conventional BCS superconductors, mediated by very high-frequency phonons involving the light hydrogen atoms,
just pushed into an extreme regime by the pressure. So you can see across all these types, conventional elements and alloys, unconventional cuprates and iron-based materials, MgV2, and these extreme pressure hydrides, we have this incredibly vast, diverse landscape of materials. Each has its own unique physics, properties, challenges, and potential.
Okay, so we've journeyed through the history, wrestled with the mind-bending physics. Now, what does this all mean for us? Where do we actually see this incredible science manifesting in technology that impacts our lives today?
Well, the most dominant application, by far, commercially speaking, is in high-field magnets for magnetic resonance imaging, or MRI. MRI is the largest single market for superconducting wire. Those machines you see in hospitals use large coils of superconducting wire, typically NBTI, cooled by liquid helium, to create incredibly powerful and extremely stable magnetic fields, usually 1.5 or 3 Tesla, though higher field research systems exist. Once the magnet is ramped up to its field, the power supply is disconnected, and the coil operates in a persistent mode. The current flows indefinitely with essentially zero decay, providing the extremely stable and uniform field needed for generating incredibly detailed, non-invasive images of soft tissues inside the human body. It's revolutionized medical diagnostics.
Yeah, MRIs are amazing. And in fundamental science, like at the Large Hadron Collider at CERN, those same kinds of materials are absolutely crucial for steering particles traveling at near light speed, letting us probe the very building blocks of the universe.
Absolutely essential. The LHC relies on over 1,200 large superconducting dipole magnets, mainly using MBTI cable, to bend the high-energy proton beams around its 27-kilometer ring. These operate at 8.3 Tesla. There are also thousands of other superconducting focusing magnets. Without superconductivity, building an accelerator with the LHC's energy reach using conventional resistive magnets would be practically impossible. It would either need to be vastly larger or consume truly astronomical amounts of electrical power just to run the magnets. Superconductivity makes it feasible. They're also using the higher field NB3SN for upgrades.
Right. Beyond the big science and medicine, what about energy and power applications? The dream of lossless electricity transmission sounds like it could completely redefine our power grids.
It absolutely could, and it's an area of active development, particularly using the high-temperature superconductors, HTS. HTS power cables, using materials like YBCO or BSCCO, cooled by liquid nitrogen, can carry 5 to 10 times the electrical current of conventional copper or aluminum cables of the same size. This offers a really promising way to upgrade power capacity in congested urban areas, where digging up streets to lay more or bigger copper cables is incredibly disruptive and expensive. HTS cables allow for much more power through existing conduits. There are several demonstration projects around the world showing this is feasible. And looking further ahead, in the quest for clean fusion energy, devices like the International ITER project absolutely rely on massive, powerful superconducting magnets using both NBTI and NB3SN to confine the incredibly hot plasma fuel over 100 million degrees Celsius, keeping it stable and away from the reactor walls. Superconductivity is an enabling technology for magnetic confinement fusion.
And for transportation, you mentioned those floating trains earlier. It still sounds like something straight out of a futuristic movie, but they're real.
Oh, very real. Magnetic levitation, or maglev, trains are a reality, particularly in Asia. The SC maglev, superconducting maglev system in Japan, is a prime example. It uses powerful superconducting magnets on the train bogies, interacting with coils in the guideway, to levitate the train about 10 centimeters above the track, and also to propel it forward using linear motor principles. By eliminating wheel-on-rail friction, it allows for incredible speeds. The SC maglev has achieved record speeds of over 603 kilometers per hour, that's about 375 kilometers per hour, making it the fastest ground transportation system in the world. China also operates maglev lines, including the Shanghai Transrapid.
Incredible speeds. And this quantum phenomenon also finds its way into really sensitive electronics and sensors, which sounds like a completely different realm of application again.
That's right. It's not just about bulk power or high fields. SQUIDs, which stands for Superconducting Quantum Interference Devices, leverage the Josephson effect we talked about, the tunneling of Cooper pairs. SQUIDs are the most sensitive detectors of magnetic fields known to exist. They can measure fields thousands of times weaker than the Earth's magnetic field. They're used in specialized medical diagnostics like magnetoencephalography, MACNIG, to map the incredibly faint magnetic fields produced by neural activity in the brain, and magnetocardiography, MCG, for the heart. Also used in geology, material science, and fundamental physics research. And perhaps most excitingly for the future, Superconducting circuits incorporating Josephson junctions are one of the leading platforms for building quantum bits, or qubits, the fundamental elements of quantum computers. Companies like Google, IBM, and Rigetti are heavily invested in superconducting qubit technology.
Okay, so we've come this far from basically a laboratory curiosity almost missed in a notebook to these incredible diverse applications changing medicine, science, and potentially energy and transport. But there's still the ultimate goal, isn't there? The Holy Grail.
Indeed. The discovery of a material that superconducts at room temperature, or let's say, easily accessible temperatures, and crucially, at ambient pressure. No need for liquid helium, liquid nitrogen, or millions of atmospheres of pressure. Such a breakthrough, if truly realized and manufacturable, would absolutely unleash a technological revolution on a scale difficult to fully comprehend. However, the path towards it is fraught with significant challenges, and it's really important to understand those.
Like the massive pressure problem you mentioned with those superhydrides. You get the high temperature, yes, but only under conditions that make them completely impractical for any real-world use outside a specialized diamond anvil cell in a lab.
Exactly. The materials with the highest confirmed critical temperatures right now, the superhydrides, only achieve this amazing state under truly extreme pressures, millions of times atmospheric pressure. This makes them fascinating scientifically, proving high TC is possible, but technologically unusable for, say, a power cable or an MRI magnet. A huge ongoing challenge is finding ways to synthesize similar hydrogen-rich materials, or perhaps entirely different classes of materials, that remain stable and superconducting at or near room temperature without needing that immense confining pressure. It's a major material science and chemistry challenge.
And then there's a whole issue of just making these often very complex materials reliably and then proving they actually are superconducting according to all the rules. I remember there was a huge amount of buzz and then quite a bit of controversy and skepticism around something called LK99 just last year.
Yes, the LK99 story from 2023 is a perfect and very recent illustration of these challenges, particularly synthesis, reproducibility, and the critical need for rigorous scientific verification. The initial reports claiming room temperature, ambient pressure, superconductivity in this lead apatite material generated massive global excitement online and in the media. However, subsequent attempts by numerous independent research groups around the world failed to reproduce the key signatures of superconductivity in materials synthesized according to the original reports. While some interesting magnetic or resistive transitions were seen by some, none could definitively confirm true superconductivity specifically, the combination of zero resistance and the Meissner effect. It really highlights how difficult synthesizing these complex, often multi-phase materials can be, and underscores why the scientific community demands robust, reproducible evidence demonstrating all the defining characteristics, not just one suggestive measurement. Extraordinary claims require extraordinary evidence, and there's also a theoretical challenge. For the unconventional superconductors, like the cuprates and iron-based ones, we still lack a complete predictive microscopic theory like BCS for conventional ones. This makes the search for new materials often more reliant on chemical intuition, computational screening, and sometimes just plain serendipity, rather than purely theory-guided design.
So, okay, let's look ahead. If we did somehow achieve this holy grail, a practical room temperature, ambient pressure superconductor, what would that future really look like? We hear about revolutions, but what about the economic realities of actually implementing it?
Well, if we had such material, and it could be manufactured affordably and reliably into usable forms like wires or tapes, the potential impact would be genuinely transformative across countless sectors. Imagine lossless electrical grids, saving maybe 10–15% of all generated electricity currently lost in transmission and distribution. Highly efficient and compact energy storage systems, like superconducting magnetic energy storage, SAES. Vastly more powerful and smaller electric motors and generators. Widespread, economically viable maglev trains for high-speed transport, cheaper and more powerful magnets for everything from medical imaging and scientific research to, perhaps crucially, making commercial fusion energy much more attainable and cost-effective. Electronics could become faster and more efficient.
It sounds like a utopia. But even with that scientific miracle, the economic hurdle of actually switching everything over seems immense. The scale of replacing our existing infrastructure is just mind-boggling.
It absolutely is. That's the crucial reality check. Even if we discovered the perfect material tomorrow, the cost to manufacture it on a massive scale, and then to replace the trillions of dollars worth of existing copper and aluminum infrastructure in our power grids, motors, and everything else, would be staggering and take decades, if not longer. So the initial impact would likely be in niche, high-value applications first, or in enabling entirely new technologies that simply weren't possible before. Think specialized scientific instruments, maybe next-generation computing, or specific industrial processes. A wholesale replacement of our current energy and transport systems would be a very long-term transition, driven by economics as much as by the science itself.
Well, what a journey. We've gone from a startling laboratory curiosity, almost missed back in 1911, to what is now really a cornerstone of modern condensed matter physics and a driver of truly transformative technologies. We've seen how its two defining properties, the complete absence of electrical resistance and the active expulsion of magnetic fields, the Meissner effect, really mark it as a unique macroscopic quantum state, unlike anything in our everyday experience. We explored the paradigm shifts in its discovery from Onnes's initial careful observation to the Meissner effect revealing its true nature, and then the high-temperature revolution kicked off by Bednorz and Muller, each step pushing the boundaries of what physicists thought was even possible.
And we've unpacked that hierarchy of theories trying to explain it. From the early descriptive models like the London equations and Ginzburg-Landau theory, which gave us our first quantitative understanding in concepts like penetration depth, coherence length, and the type A, type 2 distinction, all the way to the profound microscopic explanation of the BCS theory, finally revealing the why behind it, all the Cooper pairs formed by that subtle electron-phonon dance. This theoretical framework helped us understand that fundamental dichotomy between type I and type 2 materials, with type 2's remarkable ability to tolerate intense magnetic fields by forming vortices being absolutely key to today's most significant high-field applications. And the material landscape itself is just incredibly rich and still growing, from the conventional metallic alloys like NBTI and NB3SN that power our MRIs and particle accelerators, to the exotic high-temperature ceramic cuprates and iron pnictides that operate with liquid nitrogen, and even those extreme pressure hydrides that hint at the ultimate prize while posing immense challenges.
So as we wrap up this deep dive, here's something to maybe think about. How often do you stop to consider the seemingly esoteric, almost abstract pursuits of fundamental quantum physics happening in the coldest, most specialized labs on Earth? And yet, these very pursuits, understanding these strange quantum states of matter, are now directly shaping some of the most ambitious technological dreams for our collective future. Things like potentially boundless clean energy from fusion, or lightning-fast, frictionless travel with maglev. It makes you wonder, doesn't it? What other surprising quantum phenomenon, maybe lurking in some other extreme corner of nature or a lab experiment somewhere, might be the next holy grail waiting to be discovered?
Yeah.
Something that could emerge from scientific curiosity to fundamentally reshape our world, our technology, and perhaps even our civilization in ways we can't yet imagine. The profound and often unexpected connection between deep scientific discovery and its tangible impact on humanity just continues to astound.